Okay, salam from Saudi Arabia. Today, okay, salam from Saudi Arabia. Hardcore ferrite. Today, and this hardcore ferrite consists of one part is the hexafluoride, the other one is the hexafluoride accepted as the hard one, and the accepted as the soft ferrite. Why we are dealing with this special nanocomposites? Because you know that this hexafluoride has a high porosity and a high saturation ionization, and the ferrite low coercivity as compared with the hexafluoride and high saturation ionization.
Sorry to
What
interrupt.
we are trying to do, we are trying to combine these two properties, the magnetic properties of hexaferrite and spinel ferrite together, just to investigate changes in microelectrode capacity. And then this study was done by the collaboration of my two colleagues. One of them is Yasin Silimani, and the other one is Munir Al-Masari. Okay, we are in the same institute, and the first one is the PhD student of Munir Al-Masari. Actually, this presentation is one part of her master's study. Okay. This presentation is one part of her master's study. My presentation will include, first of all, the introduction, then application of this type of materials, and the preparation, and the analysis, or let's say characterization. Of course, under the analysis title, we will introduce structural characterization here, and also the magnetic properties of the obtained product, hard soft ferrite. Okay. Now, it's general things like that. The magnetic ferrite having hexagonal crystal structure are called as the hexaferrite, and these hexagonal ferrites have different types. But among these different types, we only concentrated ourselves on the M-type hexaferrite, and which are either barium or strontium or the lead hexaferrite. Till now, we must deal with the barium and the strontium hexaferrite because the magnetic properties of both are more important than that of the lead hexaferrite. So we mostly concentrated on this barium and the strontium hexaferrite. This is the hard part of our nanocomposite. Now let's come to the soft part of nanocomposite, okay, which is the cobalt ferrite. But among this one, you can put any transition metal instead of nickel, cobalt, manganese, and among these four, of course, you can increase the number of spinel ferrite. Example, we try to study it with the cobalt hexaferrite, which is considered as a hard ferrite. But when we say that the hard ferrite, we cannot consider it as a hexaferrite. It can be called as a hard ferrite when it's compared with the magnetic properties of the other spinel ferrite, like nickel, manganese, and iron trioxide, something. Okay, so shortly we have hard part in the first line and the soft part which is given in the second line. Now, okay, and in the crystal structure of the hexagonal ferrite or hexaferrite, it consists of the close packaging of oxygen ion layers, and among these oxygen ion layers we have barium, strontium, and the iron. Okay, now when you come to again the M-type hexaferrite, M-type hexaferrite can be considered as a solid solution, and then their formula can be given like this: MEF12O19, and then sometimes they are calling this as magnetopolyamide. As I explained before, this Me mostly barium and the strontium, but there is also a possibility of putting with lead here, but lead is not so common due to its chemical properties, magnetic properties, I'm sorry. Now let's have a look at among this between the strontium and the barium hexaferrite, the most common hexaferrite is the strontium hexaferrite, and due to that reason now we are studying on strontium hexaferrite. We did many studies. We published many papers related with the strontium and the barium hexaferrite. Now this is a new study that we are trying to synthesize harsh soft nanocomposites. Okay, and then let's have a look at the last item. The synthesizing a low-cost hexaferrite with improved magnetic and electrical properties is a still challenge for many research and industry. in recent years, okay, the number of research and of course as a result of it, the number of publication of produced from this studies, okay, is increasing year by year, okay, due to the special importance of the hexafluoride. Why? Because as I told you before, they are really important element, especially in the field of microwave absorption. Now let's have a look at another slide. So this is the general information, then the application of the hexafluoride, where we are using them, okay. Mostly hexafluoride, barium or strontium, no problem, that we are using as microwave absorbers, or also the high density recording media, and as a sensor, and for the next generation of non-volatile memory applications also they are trying to use this one. And of course this is the MI shielding material that they are using, the hexafluoride. And this part and the first and the second one more or less the same meaning, okay. So it means that both of them, hexafluoride can so you know that this our nanocomposite consists of both hard and the soft part. For the hard part, we mix them together, okay. Then of course the liquid minimum amount of water, both of them, okay. Of course we will dissolve also citric acid in a minimum amount of water after blending all of them in a mortar. Then we will arrange the pH of the solution to 7, and we will heat up to 7. We will heat it up to 1800 degree, and in that case the solution seems to be solution. The liquid is the solution. But when we continue to heat it at this temperature, I mean at 1800 degree, and somehow precipitation will start, and then it means that solution has been already converted into what? Into gel formation. Then immediately we will increase the temperature from 80 to the 300 as an average, and the combustion within this two precipitate as it was given here. Then we will do annealing process for this product. The annealing was done at 1000 or 3 to 4 is always fixed. We are just varying the amount of the spinel part. You see, the X maybe one or two. The end we synthesize 1, 2, 3, 4, and the 5 products. So we deal with their magnetic properties, and in the near future, inshallah, we will try to look at the microwave absorption properties also. Okay. And then this, this is the SAM image of one sample, which is this is true for X is equal to 1. This SAM image is true for X is equal to 1, and then you see that it is very clearly seen that there is a hexagonal plates in the morphology of the product. Now, if we continue, let's have a look at the characterization of our sample, our product. The characterization, of course, we did XRD. XRD is important for us to do identify the composition of our products, and then for this purpose, we used Ripple analysis. Okay, you see that each X-ray, the X-ray powder pattern of each sample, 1, 2, 3, 4, and 5 sample. Okay, we did Ripple analysis, and then we did phase analysis like this, and then there is no any impurity. There is no any peak that shows the presence of even a small amount of impurity. Then by using this software, okay, then we can get some information. This information given on the table, in this table right side. Okay, so we can easily calculate the crystal hard part in each composite, soft and the hard part in each composite by looking their important peaks, their major peaks here. Okay, and also for hard, then we can also calculate the cell parameters, okay, for the hard phase. Also, by the help of the software program that we are applying for the phase analysis, we can reduce the fraction of hard and soft in the structures. We can reduce the fraction of hard and soft in every nanocomposites. Okay, and then we can look at it as we calculated the cell parameter for A and for cell parameter for the hard phase, which means hexafluoride. We also calculated the cell parameters for the soft. As I told you before, the hard phase, which is hexafluoride, has a crystal structure of hexagonal, so it has only two parameters, cell parameters, A and C. And the soft part consists of spinel, which has a crystal structure of cubic. So it has only one cell parameter, which is A. Okay, and then cell parameters are given in this order. You see, for example, when x is equal to 1, which is given on the first line, and the fraction of hexafluoride part is 91.1, and the fraction of the fourth part is about 9. When you add this column and this column, and for all nanocomposite, and you will reach to 100. Okay, that is the crystal information, the crystal structure information that we can deduce at the end of our Rietveld phase analysis. And then another thing that we did, as I told you before, which is for morphological analysis. You see, when we look at here, it is clearly seen that there is a plate-like hexagonal structure, okay, in each of them, and then there is some other parts, okay, and this plate-like structure is due to the presence of the hexafluoride fraction, and the other part is due to the spinel part, okay, and then you know that we have 5 products, and then these 5 products SEM image is given in the slide, as you can see. Okay, just 1 minute, please. This is the SEM images, scanning electron microscopy of our 5 products. Now, by the help of the high resolution TM, okay, we have a high resolution TM here, and it's possible for us. We can, you see, we can look at the deep morphology. We can get the deep morphological information, and also we can look at the line spacing as it was given here. You see this calculation, and this is the selected electron diffraction pattern of for x is equal to 1.5. This all the TEM images given at the top 3 are just true for x is equal to 1.5 nanocomposite. The one which is given at the bottom, okay, true for x is equal to 2 nanocomposites. Other than this, okay, as a morphological study, we did what? We did elemental analysis. Sorry, elemental mapping, and the elemental analysis. And this is for x is equal to 2, and this is the one which is on the right side is the proof for the x is equal to 3. And then this is another proof that the chemical composition of these 2 samples are confirmed by the help of elemental mapping and the EDX analysis. This is another proof of that. Now let's come to the magnetic investigation that we did. We did a magnetic measurement at 2 temperatures. One of them, as you can see on the figure, at room temperature. The other one is at 10 Kelvin. I mean that this is the room temperature, this is the low temperature, okay, and this magnetization measurement done for each sample, okay, 1, 2, 3, 4 for each sample that we did. As you can see, at room temperature, okay, here there is no coercivity. Of course, they are not super paramagnetic, but they seems to be super paramagnetic. But when you come, you see A and the B here, okay. So it 5 samples, 1, 1.5, 2, 2.5, and the 3, all are given here, okay. Then this let's say we have some pictures, or we have some results that we obtained at the end of our magnetization measurements, okay. So this is the, let's say, shortly we can say that this is the hysteresis loops, okay, 10 Kelvin and the room temperature, okay. Now let's have a look at this right slide. And by the way, all this magnetic characterization done by my colleague, who's Yasin Silimani, who's a physicist, okay. He is responsible from magnetization part of all our study. Actually, I am chemist. I'm dealing with the I'm dealing with the chemical formula and the synthesis, and then the other 2 physics colleagues are dealing with the magnetic investigation of our sample. So this is the H maximum variation of our sample with the soft content. You see that at different temperatures, at 10 Kelvin and the 300 Kelvin, or at room temperature and at top temperature, and then this shows the variation of this hard and soft. And then this graph, which is given on the right side, is showing that at low temperature, Vmax is increasing gradually with the soft content. I mean that the X values. Okay. Now let's have a look at this. This is another indication. This is important parameter for us. Why? Because we are arguing that we have exchange coupling in our sample, exchange coupling, and the indication of presence of exchange coupling in our all products. I mean that in 5 products, okay, can be proved by the presence of the single peak here. For all that we have single peak. If the peak given on the A and the B, the A is true for room temperature and the B is true for 10 Kelvin, okay, if the number of peaks here is the more than 1, I mean that 2, let's say, this shows the absence of the exchange coupling. But we are lucky then, but by the help of these two figures, A and the B, then we can easily say that we have a strong exchange coupling between hard and the software in each composites. Okay, then I don't want to one by one because I have to explain them. Let's just have a look at the last item. This last item is saying that according to the picture given here, we can easily say that for the nanocomposite, which is X is equal to 3, okay, exhibit the highest intensity of the peak as compared to others, and it means that the highest level of let's say exchange coupling is true for X is equal to 3 nanocomposite. But when we look this A and the B, the room temperature and the low temperature curves, okay, and then these two curves simply prove that for all nanocomposite, all 5 nanocomposite that we have, there is a exchange coupling, or sometimes that we are calling this as a spring coupling in our products. Now, yes, let's have a look at the conclusion. Okay, so in that case, that we try to synthesize the nanocomposite, which is given in this formula as a hard soft nanocomposites, okay, and then successfully prepared by one put sun gel combustion pad. This is important because in some cases they are preparing hard and the soft separately, and then they are doing physical mixing to produce this compound. But this way of some disadvantages. But in our case, I mean that just by using one put sun gel combustion pathway, okay, by the help of the one run, it was possible for us to successfully synthesize all these 5 compounds. And then the second case, then the phase purity of all products confirmed by the EDX and the XRD, okay, and that class. And the VSM measurements show that all samples have hard ferromagnetic behavior at low temperature and paramagnetic behavior at room temperature. As a fourth, hard and soft conjugate system of strontium and the cobalt are confirmed by the switching the field distribution curves that I showed you before. And the present knowledge may contribute towards the development of terbium and the TP substituted strontium hexafluoride based device application along with the hard soft. I mean that the microwave absorber materials. Okay, and we published this study, I think, in 1 or 2 months before New Journal of Chemistry, Royal Society. Okay, successfully. Now this study is continuing. Why? Because by using this products, I mean that it's nanocomposite. Now we are on the way of measuring their microwave absorption properties in one university in Russia by collaboration with Professor Dr. Alex. Okay, now he is now measuring it. Inshallah, soon we will try to publish it. Okay, now I don't know whether you are familiar to Saudi Arabia or not. Okay, this is the picture of our institute. Okay, you may say that Saudi Arabia is desert area. We are lucky because we are living in part of Basra Gulf. Okay, we are near to both Kuwait and Bahrain. Actually, Bahrain is not 30 minutes from here. So this is our main campus. Our university has many districts, okay, but this is our main campus, and this is the picture from Saudi Arabia. Now, thanks for your listening and participation. If you have any question, that I can try to answer your question. Again, thanks for the participation. Thank you.
Yeah, okay. I was wondering, among all the composites that you have described, which one has the more desirable properties for your applications?
Yeah, but right now we cannot answer this question
For the applications that you were
it's,
commenting, absorption of
yes,
electromagnetic waves.
yeah. Right now we don't have any microwave absorption data of our sample. Now they are doing this measurement, but according to the magnetic data that we obtain, okay, we are assuming that all sample have somehow magnetic absorption properties. When we get the result after the measurement, then we can say something on that. Right now, not possible.
But are these materials already used in applications?
Yeah,
This
yes, of
kind of
course.
composites?
Yes, as a hard soft nanocomposite, okay, with having exchange, they are using this, but this chemical, this is a new area. Sorry, this is a new area. But what is the novelty of our study? This is the first study in which we use TM and TB as a rare earth element in our synthesis. Then we are wondering their effect.
Okay, thank you.
Oh, no, welcome.
Then,
thank you.
If there's no more questions, we thank the speaker again.
Thank you. Thank you for your participation and contribution. Thank you.